Hello everyone, welcome to my YouTube channel. Today we'll discuss about role of nanotechnology in biomaterials and their applications and tissue engineering. Okay, so nanotechnology I have briefly explained in the previous classes. I'll just give a brief introduction here. Nanotechnology is a technology which is nothing but exploiting the nanomaterials applications, right? So here the nanomaterials, to whom we call nanomaterials, if the size is following 0.1 to 200 nanometer or 1 nanometer to 200 nanometer, then only we are calling them as a nanomaterials. And the science at this particular level, 1 to 200 nanometer, usually 100, but sometimes some cases you consider 200 nanometer, the science behaves differently. It's not same as bulk. For example, in bulk, what is the color of gold? It's gold or yellowish gold, right? But when it comes to the nanoscale gold, around 80 nanometer we are having purple in color, around 20 nanometer we are having red in color, around 10 nanometer again we are having yellow, purely yellow in color. That, see, what I am trying to explain is the properties totally get different at nanoscale. Take for example optical property, that is also different, mechanical property different, electrical property different, thermal property different, the melting point, everything changes at nanoscale. That's what you should remember. Okay, why changes? Because of its effects, quantum effects. The reason is simple. We know that the normal physics, the old physics and new physics. The old physics we call classical physics, new physics we call quantum mechanics. So physical physics, normal physics, quantum mechanics. Quantum mechanics in the sense the physics at atomic scale and molecule scale, whatever we study, the science changes there. Atomic science is totally different from the normal science. So that's why we are having the separate field, that is new physics, quantum mechanics. For nanomaterials, since they fall between molecules and the atomic scale, in between the range is there. Molecules are 10 to the power minus 8, whereas nano is 10 to the power minus 9, whereas the atom is 10 to the power minus 11 or 12. So in between this 10 to the power minus 9 is there. So that's why we are having the nanostructures which are also following the laws of quantum mechanics. Because of this we are having different properties at nanoscale. So that's why nanoparticles plays a very important role in biomedical field, because we can tune any property. For example, as I told you, if I want gold in red color, I can have it in nanoscale. If I want gold in yellow color, completely yellow in color, I can have it. If I want purple in color, that also I can have it. That means I can have different properties at different size. Understanding? So that's what so much cool about nanotechnology. So I can have any property at any time, right? So nanoparticles have been used to serve various functions in tissue engineering. So if you want to know more about nanotechnology, I have a separate playlist for a separate subject, that is nanotechnology, in my YouTube channel. You can just refer, or previous topics also you can refer. So nanoparticles have been utilized very widely in the tissue engineering. So materials at nanoscale exhibit excellent properties which makes them used for enhancement in biological, electrical and mechanical properties. Whatever the properties are there at bulk, when you reduce the same material to the nanoscale, it will give you 10x to the 100x better properties. Okay, so nanoparticles, for example, if I want to reduce any nanomaterial on a imagine a brick which is normally prepared by the macromolecules. Now those macromolecules, I have A brick which is prepared by the macromolecules. I have B brick which is prepared by the nanotechnology. How? These macromolecules, I will reduce it to nanoparticle size. That means every particle has to be nano. Then I make a brick out of it. So when compared with the hardness, this brick B will have more hardness, 10x harder than this one. Why? Because that is made up of nanostructures. Because as the size scale goes down, the hardness will increase. So the surface to volume ratio increases. All these things will play a very important role at atomic or molecule scale and in between this nanoscale. That's why the nanomaterials are totally different, and they will enhance every properties. So nanoparticles find amazing applications in drug delivery, gene delivery, DNA transfection, viral transduction, pattern of the cell, and to facilitate the growth of the various cells of various types of the cells or tissues, and also to molecular detection and biosensing. All these applications nanotechnology is there. So the use of right type of nanomaterials in tissue engineering can significantly enhance the biological, mechanical and electrical properties of the scaffolds, and as well as they can serve various functions depending on the applications describing the following. So the first thing, biological property enhancement that can be increased to increase cell proliferation rates can be done by nanotechnology. Enhancement of the mechanical properties done by the nanotechnology. Electrical properties also done by the nanotechnology. So three properties: biological, mechanical and electrical properties. Let's see one by one. So biological property enhancement, that is to increase the cell proliferation rate. Why cell proliferation has to increase? Because in tissue engineering we want to develop the cells as fast as we can. So proliferation rate should be increased. So we know that nanoparticles is increasing all the properties. Let's apply nanotechnology here. That's it, simple. In particular, two types of nanoparticles have been, namely it has been used, that is graphene nanoparticles and titanium dioxide nanoparticles. These nanoparticles have been widely used to enhance the cell proliferation rates of a bone and cardiac tissue generation respectively. That means for graphene nanoparticles has been used to enhance the cell proliferation for the bones, whereas for heart or cardiac tissues titanium dioxide nanoparticles have been used, and they have proven very well. So graphene nanoparticles have shown a superior biocompatibility compared to the normal particles biomaterials, and the ability of surface modification, which has resulted in interesting biomedical applications. So graphene nanoparticles in bone tissue engineering, it was first observed that the graphene nanoparticles promote osteogenic differentiation of an osteoblast precursor cell line, that is MC3T3E1. So that was the first case study. Another case study was reported that the graphene nanoparticles they can promote osteogenic and as well as adipogenic differentiation of the mesenchymal stem cells. That means they are enhancing this particular differentiation. So in both studies, it was osteogenic differentiation is dependent on the size of the graphene nanoparticles. For example, at 100 nanometer there is a differentiation, at 80 nanometer different, 60 different, 40 different. So when we are reducing the size, so most of the times the property will be enhancing. So I can have whatever the rate I want. If I want the degradation rate to be too much, I can have. If I want the degradation to be very slow, that also I can have. Similarly, I can have the cell differentiation faster or slower. Whatever I want, I can have that. That is the coolness about nanotechnology. So studies also demonstrated that 20 to 40 nanoparticle size nanoparticles favorable for more effective for MC3T3E blast-like cell structures, whereas 30 to 50 nanometer for human adipose derived stem cells. So here two things we discussed now. Here, for example, MC3, this is one for mesenchymal stem cells. Osteoblast precursor, mesenchymal stem cells. So for mesenchymal stem cells, these are adipose derived stem cells. It took the best nanoparticle size was 30 to 50 range, and for MC3T3E1 the size was 20 to 40 nanoparticles. That means at that particular size particles they showed a better enhancement there. And see, that's what I'm telling. The same different, these are two different properties, right? Two different applications, but the same nanoparticles can be used for both applications by just changing the size. So size matters. So titanium, that was about graphene nanoparticles. Next, titanium dioxide nanoparticles. In other study, titanium dioxide nanoparticles were added to the scaffolds in which the human embryonic stem cell derived radiomyocytes showed enhanced cell proliferation. In the introduction only we told graphene nanoparticles for bones, whereas titanium dioxide nanoparticles for cardiomyocytes or heart cells or tissues. So here in other study, titanium dioxide nanoparticles they were added along with the scaffolds, like growth factor what we as in the first module what we discussed, the same thing. So in which the human embryonic stem cell derived cardiomyocytes showed enhanced cell proliferation. That means this cardiomyocytes, that means heart cells, they showed a better enhancement cell proliferation. That means the faster differentiation. So thus incorporation of certain types of the nanoparticles into scaffolds can significantly alter the biological properties of scaffolds and thus help in tissue engineering. So that was about this thing. what do you say, biological property, right? Under biological property, two things we discussed, that is first thing is graphene nanoparticles, then titanium dioxide nanoparticles. Next we are having the enhancement of mechanical properties. So as we know, take one example, 5 meter, you take 1 meter of 1 meter stick, try to break it, you can easily break it, and reduce it to the just half meter, again still you can still break it, a little bit extra effort you have to add. Reduce that to the 10 centimeter, that now it will be very hard to break it. So here what you observe, as the size is decreasing, what is happening, hardness is increasing, that's what, and it goes to the nanoscale, it will be extremely hard. So nanoparticles, embedded nanocomposites, polymers, both in the form of hydrogels and electrospun fibers, have exhibited superior mechanical properties for tissue engineering applications compared to the scaffolds without the nanoparticles. That means the scaffold with nanoparticles has got superior mechanical properties with, when compared to the scaffolds which is not having the nanoparticles. So for example, titanium dioxide embedded biodegradable patch showed a higher tensile strength, that is one of the mechanical property, in reinforcing the scar after the myocardial infarction. So here the higher tensile strength is very important for myocardial infarction, because after the scar, this thing and all, no, so that has to be recovered soon. So that property was increased along with the nanoparticles. Without the nanoparticles, it was not increased much. So next, carbon nanotubes, that is CNTs, have also been used to enhance the mechanical properties of the polymers in tissue engineering applications. So CNTs, that is carbon nanotubes, reinforce the polymer surfaces or polymers, especially due to their remarkable mechanical properties, tensile strength and fiber-like structures. We know that polymers lack in mechanical property that can be overcome with the help of nanomaterials. We know that the carbon nanotubes is one of the best nanomaterial which has got the best reinforcement property that is just used along with the polymers. So you will get whatever the mechanical property the materials are having, like metals and ceramics, same thing can be achieved with the carbon nanotubes along with the polymers. That is actually a great thing. So recently carbon nanotubes were added into the polylactic acid, that is PLA blends, that is again a polymer, and were electrospun into the nanofiber mats. So it was found that, what was the result? So it was found that they had amazing biocompatibility and as well as osteoinductive potential as compared to the PLGA gelatin nanofibers. So this is the recent studies along with the compared to the PLGA gelatin nanofibers. When you add CNTs along with a PLA, that is PLA bar CNT, that composite has given amazing biocompatibility and osteoinductive property or a potential. So that's what, if you keep on changing the nanomaterial size, you get a different properties, applications. If you're changing the materials also, you will get a different applications. So that's what the best thing in nanotechnology. That means whatever we want, we can achieve with the nanotechnology. That was about mechanical property. Now coming to the last part of the topic, that is enhancement of the electrical properties. Electrical properties plays a very important role because in tissue the conduction is very important. Signal transaction will happen from cell to cell. That is also happens with the electrical impulses. So various nanoparticles have been used in the to enhance the electrical properties of the scaffolds, which can highly beneficial in cardiac myocytes, cardiomyocytes or cardiac cells. So for example, we know that the highest conductive material on earth so far is again a nanomaterial, that is carbon nanotubes. That means we are having a high thermal conductivity, high electrical conductivity, high mechanical properties like stiffness and all other things in nanostructures only. Okay, we are having the same amount, same bonding, that is carbon-carbon covalent bond in graphene, carbon nanotubes, buckyballs. So imagine so much hardness we are achieving at nanoscale. So studies were carried out using gold nanostructures which were integrated into the scaffolds to boost the magnetic conductivity and develop an electrical signal between the different cardiac components. So this was the case study. So that was one of the case studies where gold nanoparticles have been used and they got obviously the better results. So next we are having GNP based electrospun, that is graphene nanoparticles based electrospun fibrous scaffolds. And that means along with the scaffold the graphene nanoparticles are added. Okay, they were reported to be a functional for cardiac tissue regeneration. Next we are having gold nanowires. They have also been used as conductive material alongside scaffolds to enhance the electrical coupling between the cells. Next we are having studies have also highlighted, again a lot of case studies are there. So studies have also highlighted that the use of the CNTs, highest conductive material on earth, so the carbon nanotube in polymer composites, they can significantly improve the conductivity to promote the cardiomyocyte function. The better the conductivity, better cardiomyocyte functions. So it is clear that conductive nanomaterials have a promising future in cardiac applications. Compared to with the help of the previous studies, all these studies, we can surely say that nanomaterials can bring a promising future in cardiac applications. So that's it. If you have any doubt, please let me know. That's the end of the module 3. Module 4 we will take in the next class.